So for our Physics 122, 132 project, we decided to take a trip to the beach, and we calculated some basic measurements about ocean waves. So the first couple things we found, we got the crest, which was 29 centimeters. We got the trough, which was 14 centimeters. And from that, we were able to calculate the wavelength, which ended up being 15 centimeters. And the main thing we decided to do at first is we calculated the velocity. So we would decide to calculate the velocity. So by doing that, we're going to use the standard equation. Velocity is equal to wavelength times the frequency. And while we were out there, we decided to calculate the period and the wavelength. So we found our period to be approximately 16.8 seconds per cycle. And then we had the wavelength, which was 31.7 meters. So the wavelength is standard, so we can just plug that in. But with the period, we need to take the reciprocal, so we need to do 1 over 16.8, and that'll give us our frequency. So we have frequency equals 0.06 seconds. So that is our frequency, and then this is our wavelength. So in order to calculate the velocity, we can just take v equals lambda times frequency. So our lambda is 31.7 meters, and our frequency is 0.06 seconds per cycle. And we multiply that, and we get approximately 6.34 meters per second as our velocity. So now that we have our velocity, we kind of figured that since this is a typical wave, it's a typical ocean wave, that we'd be able to apply the standard equation, or the standard wave equation. Yeah, I gotta throw that wave in there. So with that, what we decided to do is that equation is amplitude times sine kx plus omega t is equal to x of t. So we have our amplitude already, which we previously found. So that was 15 centimeters. So we're going to have 0.15 meters there. And now we have to calculate k, and we have to calculate omega. So in order to find k, we know the equation that k is equal to 2 pi over lambda. So for that, we can just have 2 pi, and then we can plug in our wavelength. And our wavelength was 31.7 meters. So we get k to be about pi over 31.7 divided by 2. And that gives us about 15.8. So that would be our k. And then now we have to find omega. So we know omega equals 2 pi over the period. So once again, we just have our standard 2 pi. We can divide that by the period, and we remember the period is 16.8. I could write seconds per cycle in there, but I'll leave it out for now. So then we end up getting omega is equal to pi over about 8.4. So now we have these two variables, so we can plug them into this standard equation, and we'll do that right down here. Now we have 0.15 meters times sine of k, which is pi over 15.8 times x. And see this plus right here? This is actually supposed to be a minus, because in the video I previously showed you guys, we see the waves traveling to the right. So we need to remember that and take that into consideration. So it's going to end up being minus omega t. Our omega is pi over 8.4. let me just rewrite this out clearly at the bottom of the paper here. And this is equal to x of t. So another thing that I didn't really address is sometimes in this equation here we will have a lovely phi, and this phi kind of just represents our phase shift. And what we're assuming for this video is that there is no phase shift, so we're just going to assume it's kind of a standard wave, so we're just focusing on this original sine of kx minus omega t equals our x of t. And what we ended up doing is we found this nifty grafting tool, and we can graph this equation in there, and it gives us a basic sine curve that could be very similar to what our ocean wave looks like.
So here's the basic graphing program that we used. We have our standard wave equation, and we plugged it into this program. So we have our amplitude being 0.15. We have our k as pi over 15.5, and then we have our omega as pi over 8.3. So after we plug all of that in, it gives us this sine wave, and we're still assuming there is no phi or phase shift, and it just gives us this basic sine curve that we can assume and see to be our ocean wave.